Time series analysis. So previously we had learned something called the multiple linear regression, right? Now previously we had learned something called the multiple linear regression, right? In multiple linear regression, how it works is y is dependent on multiple independent variables. So y is the dependent variable which is dependent on multiple independent variables. Let's say a1 x1 is the first independent variable, then a2 x2 is the second independent variable. Like this, let's say there are n independent variables on which y is dependent, right? This is how multiple linear regression worked. Now friends, these were certain cross-sectional values or fundamental values in terms of economics. For example, let's say if y represents the stock's price, then x1 might be return on equity, x2 might be the experience of the managers, right? Like this. These are fundamental factors. These are not time sequence factors, for example. Now, if you go to Google and search, let's say, XYZ share price. If you search, let's say, XYZ share price, you'll come up with something like this. There will be a vertical axis where the prices will be plotted, and there is a horizontal axis where the time will be plotted, right? Let's say 1 month, 3 months, 6 month, 5 year, 10 year, like that, right? And a curve like this will be visible to you. Something like this, right? Now friends, this kind of a curve which is plotted against time. So here P is behaving as if it is varying with respect to time. This kind of a format of plotting is called a time series format. This kind of a plotting format is called a time series format. Time series. Right friends? This is called a time series. Now, time series can be represented in multiple ways. Let us take two basic examples. The first kind of model that we'll discuss is the linear trend model. So linear trend model, how does it look like? Basically, this is very similar to a linear regression model, friends. Here, the dependent variable y is dependent linearly on time. That is, y is equal to b0, b1 multiplied by time period plus, let's say, some error. Okay, b0 is the intercept. That is the value of y when t is equal to 0, and b1 is the slope. That is, with every change in t, the degree to which y changes, the extent to which y changes. The higher the slope, the higher the extent of change with every change of t, right? And the error obviously is that part of y which is not explained either by the intercept or by the slope or by the time period, right? So we are through with this. We have learned something like this in linear regression also. Here the only thing is the independent variable is time or the time period. Therefore, for t is equal to 0, y predicted or y hat is equal to b0, right? Because t is equal to 0. Then at t is equal to 1, y predicted is equal to b0 plus b1 because t is equal to 1. For the second time period 2, y predicted is equal to b0 plus 2 into b1 because t is equal to 2. Like this it goes on, right? This is how the linear trend model is represented, and this is the simplest form of model you can say of a time series. The second model we'll look at is a log linear trend model. Let's see how that looks like. Let's say the dependent variable y varies exponentially with respect to time. So y is equal to e to the power b0 plus b1 into t. This is, let's say, the equation. Okay. If we just rearrange the equation a little bit, this becomes natural log of y is equal to b0 plus b1 multiplied by t. This is called a log linear model. Why? This side it is logged and this side it is same as linear. So this is called a log linear model. Similar to the previous one, we can find out each of the values for each of the time periods, right? B0 is the intercept, I, let's say, we call it. B1 is the slope, right? Just to make sure that we know the concepts of intercept and slope, let me again revise those concepts. Let's say the vertical axis is representing y and the horizontal is t, right? Now we have two regression lines. One is like this and the other is like this. Now let's say the green one is line A and the red one is line B. Which one has a higher slope, friends? Obviously line B. That means B1 for B is greater than B1 for A. That is, the slope is higher. That is, for every change in T, the change in Y is higher for B. Right? If you want to test it or verify it pictorically, let's say the time changes from this point to this point. Now, if you measure the change of Y was here, then it went here, right? For line A, this is the change. This is the change in Y or del Y for A. And for B, what was the change? The previous position was here and the ultimate position was somewhere here. So the total change is this much, del YB. Now you can visibly see that del YB is greater than del YA. So the slope defines with every unit change of time what is the change or what is the extent of change, what is the magnitude of change of the dependent variable or Y. So we have understood what is slope, right? What is B1? We have understood. Now what is the intercept, friends? You can see in line A, at t is equal to 0, the value of Y is here, right? For line B, at t is equal to 0, the value of Y is here. So the Y being predicted for line B at t is equal to 0 is less than the Y predicted for A at t is equal to 0, which means the intercept for A is greater than intercept for B. Again, let's check it once more. This is A, intercept is this much. This is B, intercept is this much. Which one is more, friends? Obviously, B0 for A is more and B0 for B is less. So, intercept of A is more than the intercept of B. Intercept is what? The value of Y when the independent variable or time is equal to 0. This is the value of the intercept or B0. Now let's move on with our discussion, friends. When is a log linear model used, friends? So let's say a database is working like this. This is, let's say, the data. Now you are trying to fit a linear model to it. You try fitting this one. Does it work? No, right? Not the best fit. You try fitting this one. Well, it works for the higher results, but it fails to work for the lower results. So this one also doesn't work, right? So what do we do in this case, friends? Clearly, if we draw a line like this, it seems to work better. And this is nothing but an exponential equation, right? So an exponential equation means y is equal to e to the power b0 plus b1t, right? Now you do not want to use the exponential equation. You do not want to use it. You want to convert this database into something linear. So what do? You rearrange the equation. You rearrange this equation to something like this. So this becomes natural log of y is equal to b0 b1 to the power t, right? So in this database, the vertical axis is y and the horizontal is t. Now you make a change. What change? You change it to natural log of y. then how does the database become, friends? This becomes something like this. When you take vertical axis as the natural log of y instead of y only, then the line becomes like a linear line. This one. Now the regression is much more fitted for a linear equation. So your desire for using a linear regression also is fulfilled, and the data is also not, and the data fit or the regression fit is also good, right? So this is when you are trying to use a log linear model. That is when you have a exponential kind of a pattern when you are using the simple data y. What you do is you change it to natural log of y, and the data behaves like a linear data only. So that is what we call a log linear model, friends. Testing for serial correlation for trend models. So friend, trend models means y varies with time, right? Y is a function of time, nothing else but the time period. This is the simplest kind of time series model that we have discussed already in the form of linear models and log linear models. Now friends, we are here to test for serial correlation errors in a time series trend model. Okay, so how do we measure that? Now friends, there is a test statistic called Durbin-Watson statistic. Now the value of Durbin-Watson statistic ranges from 0 to 4 approximately. Okay, a value, let's say around 1.5 to 2.5 is considered okay. That means here there is no major serial correlation. No major serial correlation. But let's say if the value is 0.5, that is significantly less than 2, then this means positive serial correlation. And if the value is, let's say 3.5, that is significantly above 2, the implication is negative serial correlation. That is significant amount of negative serial correlation. So 1.5 to 2.5 or a mean value of 2 is ideal for a Durbin-Watson statistic value. If it becomes far less, it means positive serial correlation. If it becomes far more, it means negative serial correlation. So this is how we test for serial correlation in a trend analysis. Now friends, we'll move into a little more complicated version of time series, which is called the autoregressive model. Let's see what that is.